In section 1.5.2, we'll be talking about the dimension of a vector space. So the goal is really to define the dimension of a vector space and then see some examples. All right, let V be any vector space. The dimension of B is, we'll use dim V, and that's going to be the number of elements in any basis of V. All right, so we'll have a finite number of elements, and that's going to be finite dimensional, or we'll have infinitely many, and then that's going to be infinitely dimensional. Let's do example 1.5.5, find the dimension of the following vector spaces. And so to be able to do that, I need to be able to find a basis for any of them, but for these we have a standard basis that will work. So a basis for 2 times 3 matrices, I'm going to take each entry. It's going to give me one matrix by putting a 1 in that entry and zeros everywhere else. So I have 2 more, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 0, 0, 1. All right, so I have 1, 2, 3, 4, 5, 6 element, and so it's the number of elements in BM23, and so that's 6. All right, for M by N matrices, there are M times N entries, and so B, M, M cross N will have M times N matrices in it, 1 for each entry, and so the dimension of M, M cross N is M times N. Notice that it's compatible for the 6 that we got here. 6 is indeed 2 times 3. All right, Pn. The basis we had for Pn was 1x x squared x to the n. All right, so we have n elements here, and then x to the 0 would be plus 1. And so the dimension of Pn would be the number of elements in Bpn, which is n plus 1. Let me put it here. That means the number of elements. That's what I'll use for this class. All right, so for P infinity, we had 1x x squared, and it kept going forever, and so the dimension of P infinity is the number of elements in BP infinity, and that's infinitely many. For infinite sets, it's often preferable to actually be more precise and just say it's infinite. There are different sizes of infinity. In this case, since I can list the elements, it's countable. And so this would be a countably infinite set, and the dimension would be countably infinite. Don't have time to go over different sizes of sets, so that's part of the reason we're handling infinite sets, infinite bases, infinite subsets, and linearly independent things. We're handling it a bit, but not too much. It's very interesting and very cool, but it would take about half the class to define it properly. All right, at first, it's not clear that the dimension of a vector space is well defined, since a vector space has many different bases. So we said it's the number of elements in any basis, but how do you know that all the bases have the same number of elements? So that's what we need to show. We need to show that all of its bases would have the same number of elements. The next theorem will prove it. All right, so in the next video, we'll actually prove that any basis for a vector space has the same number of elements.